Now, how do we classify these foliated rocks? We start with the metamorphic grade, low grade to high grade to ultra high grade. And what we're going to see is a change in crystal size. Crystals get bigger. Again, we'll start with a shale precursor. Microscopic minerals are going to get larger and larger as the metamorphic grade increases. The type of foliational change is a function of the changing crystals and their orientation. Now we can observe banding. This banding is going to be characteristic of higher metamorphic grade rocks. We're going to call these things based on their grade: slates, phyllites, schists, gneisses, and migmatites. Here we have an example of a foliated texture. The micas are all lined up, and we can see some porphyrioblasts, large garnet crystals that are growing within these micas. This would be potentially gemstone quality pair of garnets. And from the color, it looks like it's the garnet pyrope. This is my kitchen countertop. You can see garnets here pretty readily. You can also see a shininess, a schistosity to this, and a swirly, oozy kind of look as well. So what this represents is a schist that is transitioning past a gneiss into a migmatite. And just another shot here, large quartz bleb. You can see the texture here that's induced on this rock. This is blasted with high pressure water to give you this texture. So the harder minerals are going to be left behind, sticking up a little bit, and the softer minerals are getting blasted away by the water. And just one more. Here you can see where a layer of quartz has been deformed as the rock is transitioning to the liquid phase. You can learn a lot by going to the kitchen. This is an example from the real world outside. This is from a town in Greenland known as Nuuk, N-U-U-K. So this is a banded gneiss. Much of Greenland is made up of this kind of rock, this gneiss. And just a picture from the beach located near that last image. And large bands of albite, plagioclase feldspar here, mixed in with some chlorite and some biotite, and some quartz blended in here as well. So this is a very typical looking gneiss and a very typical beach in Greenland. Now we'll talk a little bit about granoblastic rocks. These are non-foliated metamorphic rocks. We've been talking about the crystals lining themselves up, and that's because of directed pressure. If there's confining pressure, the same from all directions, we end up with non-foliated metamorphic rocks that are composed mainly of crystals that grow in equant shapes, such as cubes and spheres, rather than platy or elongate shapes. Those garnets that we saw in the last image may have grown in one of these non-foliated metamorphic rocks. How do we name these? What do we call them? The nomenclature of granoblastic rocks includes hornfells. These are generated by high temperature contact metamorphism. A hot igneous body comes into contact with some pre-existing granite perhaps and generates a hornfells. A quartzite. These are very hard rocks, the hardness of quartz, which is 7 on Mohs scale. They're made of interlocking quartz grains. The initial sand grains are fused together. Marbles are the same kind of rock, but made of calcite crystals instead of quartz crystals. So a marble has a hardness of 3 because calcite has a hardness of 3. Because they're interlocking crystals and they're fairly soft, people use marble to carve images, statues. Greenstones are metamorphosed mafic rocks with chlorite. The chlorite is a green mica, so the presence of the green mica turns the rock green. This is what geologists look for when they're out for gold. You're looking for gold, you might look at a greenstone belt in a continental interior, ancient continental interior. Amphibolytes are composed of amphiboles and pyroxenes. This implies a medium to high grade. These are high temperature minerals, single chain and double chain silicates. They require medium to high temperatures. And then granulites. There's a granofell. High-grade metamorphism of shale, sandstone, and igneous rocks. These are coarse grain. They'll look like a granite. So how do we tell these apart? In very simple terms, foliated metamorphic rocks are distinguished by slaty cleavage, schistosity, or gneissic foliation. The mineral grains show preferred orientation. We're going to call these things slates, phyllite, schists, and gneisses. The parent rock is most commonly shale or sandstone. The non-foliated granoblastic rocks are granular, characterized by coarse or fine interlocking grains, little or no preferred orientation. That's because the pressure is confining. It's the same from every direction. It's not directed as it is in the foliated. Types of rocks we would observe would be hornfels, quartzites, marbles, argillites made of clays, greenstones, amphibolates, granulites. The parent rock for hornfels, shale and volcanics, quartzite, quartz-rich sandstone, like a quartz arenite. A marble comes from limestone or dolomite, dolostone. Argillite comes from a shale precursor. Greenstones come from basalts. Amphibolites come from shales and basalts. And granulites come from shales and basalts. Porphyroblastic metamorphic rocks, which are large crystals set in a fine-grained matrix like the garnet in the schist we just saw. These can occur in rocks that range from slate to gneiss in metamorphic grade, and the parent rock is typically a shale. So here we have a quartzite. Again, probably started out as a quartz arenite, a beach sand that had eroded away all the other minerals except for quartz. And then we bake it and fuse those grains together. So a thought question for this chapter: how is slaty cleavage related to tectonic forces? What forces cause minerals to align with one another? Going back to that image of foliated minerals, we can see that the grains are growing perpendicular to the directed pressure. It's easier to grow perpendicular to the force. So you grow not into the directed pressure, but with the directed pressure. And this ultimately causes the minerals to line up with one another. The directed pressure lines all of the minerals up, not just some of them. So here we have an example of some quartzites. This is from a town known as Gardar in Danish and Igaliku in the native Inuit language. This is a structure that was built about 1,000 years ago by Vikings. These are blocks of quartzite that were used to fortify this structure. Still standing after 1,000 years, must have been important. This is where they stored cheese and polar bear skins. Those were major commodities for the Vikings to trade back to the king in Norway. How they hunted the polar bears, I'm not really sure. The craziest thing, if you want a crazy story, is the Vikings actually brought live polar bears from Greenland and Iceland back to Norway for the king's amusement. How they caught a live polar bear and kept the bear and themselves alive in an open boat sailing across the North Atlantic, I don't know, but it should make a good movie. Okay, now we're going to talk about regional metamorphism and metamorphic grade. Grades of metamorphism include low, intermediate, and high. That's pretty easy to keep track of. Mineral isograds are zones of change, zones of the same minerals. Index minerals are going to reflect pressure and temperature conditions, geobarometers and geothermometers. Groups of 2 to 3 index minerals are required to form an isograd. Here we see an example from the northeastern US where we had a previous collision with Africa and Europe. That collision between the continents generated heat and pressure. That heat and pressure generated a range of zoned isograds that allow us to define low-grade, medium-grade, and high-grade zones in these rocks, these previously existing rocks. So where the pressure is greatest and the temperature is greatest, the site of the collision, we have the solomonite zone. The solomonite is a common metamorphic mineral. It looks like quartz, but it's rectangular in outline. So based on that alone, it's not quartz. The medium-grade rocks we observe include starlite, the crossed crystals, and garnets. We've seen both of those. Low grade contain biotite and chlorite zones, green and black. And then we have the unmetamorphosed rocks just across the Hudson Valley, which is roughly here. Okay, so now putting the rocks on this temperature pressure diagram, we start out with a slate, we heat it up, we generate a shiny surfaced phyllite. Let's get the sheen, increasing the temperature further. We go to intermediate grade with a schist, very, very shiny large micas. Crank up the temperature a bit more, and we enter high grade. We have big, blocky, foliated minerals and a gneiss, and then we'll take it all the way to just about the melting point. We end up with a twisted, tortured looking swirly rock. Now, if we take this phyllite and instead of increasing the temperature and pressure, we just increase the pressure. We're pushing it down a subduction zone maybe, or we're squeezing a continent into it. That change in pressure without a change in temperature will still induce a metamorphic change here. We're going to go from a low-grade phyllite to an intermediate grade blue schist. So the color is going to change from kind of plain, dark, medium greenish gray to bluish greenish in the blue schist. Now we're going to take a look at two different precursor rocks. We're going to take a shale and metamorphose it, and a mafic rock and metamorphose it, and see what we get. Starting with the shale, low-grade diagenesis is going to occur and force development of green schists. These are going to be chlorite-rich, again, green mica. As the temperature goes up, we transition into white mica, which is going to be mostly muscovite. Therefore, the rock will have a kind of a whitish, greenish look to it, becoming more white. Increasing the temperature further, we're going to see the appearance of biotite. So we've gone from green mica to white mica to black mica. And then the appearance of garnets, starlight, and kyanite is going to be very characteristic of the intermediate grade. Increasing the grade further to the granulite facies, we end up with the appearance of the mineral solomonite. Albite, the sodium-rich plagioclase, can be common throughout this whole sequence. Now moving to a mafic rock, like a basalt, at low-grade conditions, we're going to generate a zeolite. Zeolites are weird minerals that have a lot of potential for storing energy, for storing water. They do all kinds of weird stuff. We use them for water softeners now, but there's actually tremendous potential for storing heat for commercial purposes. That's another story. So we're going to take that basalt, we're going to go through the zeolite phase to the chlorite, and then the epidote phase. This is a dark green mineral usually. Down to garnets appearing in the intermediate, and then overlapping a bit with pyroxenes. Pyroxenes becoming much more common in the higher granulite facies. We're going to see a transition in the plagioclases, though, from sodium-rich, so the white plagioclases here, to light gray, medium gray, dark gray, blue, dark gray, black, as we go from sodium-rich to calcium-rich. And the minerals generated in each facies, starting with green schist, we're going to have muscovite, chlorite giving it the green color, quartz, and albite. That's in the shale parent. In the basalt parent, we have albite, epidote, and chlorite. The low temperature minerals are going to come out first, albite, high temperature later on. Amphibolites, muscovites, biotites, garnets, quartz, albite, starlight, kyanite, and solomonite. Going to be a medium grade or intermediate grade igneous rock produced from a shale parent. As we go into the granulite facies, we see garnets appearing. They become larger, solomonite, albite, orthoclase, quartz, biotite. And then the eclogite facies, the high grade metamorphic rocks, we'll see garnets, sodium-rich pyroxenes, quartz, coesite, which is a polymorph, and kyanite, which is a blue, characteristically sky blue bladed mineral. Starting with the basalt parent, we have albite, epidote, and chlorite in the green schist phase, transitioning to amphiboles like hornblende, plagioclase, feldspar. The intermediate amphibolite phase, that makes sense, amphiboles. The granulite phase is going to contain calcium-rich pyroxene, calcium-rich plagioclase, feldspar, becoming darker, and then the eclogite, sodium-rich pyroxene, and garnet is going to dominate. And that's all illustrated here in another pressure temperature diagram. Zeolites stable at low temperature, low pressure, which is why we will use them in our water softener or maybe to store heat under a house. I wouldn't do that. Some people are trying it, but there are some problems with that. So we dry these out by forcing them down into higher pressure, higher temperature regimes. The water from the zeolites is given off. And the result is we go down a subduction zone. We're increasing the pressure, but not the temperature, producing blue schists. If we increase the temperature and pressure, we go to green schist phase, greenish colored rocks. Increase that temperature further, maybe melting the rock partially, we enter the amphibolite phase. And then cranking the temperature way up without increasing the pressure substantially, we end up in the granulate phase. And then contact metamorphism, hornfells are going to be up here in the low pressure but widely varying temperature range. So hornfells are stable between a little less than 200 degrees and up to close to 950 degrees, but always at low pressure. What this means is metamorphic facies correspond to particular combinations of pressure and temperature, geobarometers, geothermometers. Therefore, we can look at these rocks and reproduce tectonic activity in 3 dimensions in the past, which is kind of cool if you're into that kind of thing. Metamorphism is going to occur in or near plate interiors, if the temperature is high enough, at divergent plate margins, where the temperature is going to be high, the pressure is fairly low, at convergent plate margins, where temperatures and pressures can be low or high, usually high pressure, relatively low temperature, and at transform plate margins, where it's going to be more fluid dominated. Okay, so as we move rocks through different pressure temperature zones, we're going to change them. So we start out with a low pressure, low temperature body of rock. We're going to increase the temperature, increase the pressure, change that rock, and then we're going to push that rock up. As we push that rock up, it has gone from low temperature, low pressure to high temperature, high pressure, back to low temperature, low pressure. It's going to become an increasing metamorphic grade here and decreasing metamorphic grade here. So what we see during metamorphism, the rock is going to record the story of itself. This includes the history of burial and exhumation, the burial of the rock, and then the digging up of the rock. So during metamorphism, garnet crystal grows. The composition of the growing crystal changes as the temperature and pressure change around it. So we end up with a zoned crystal. As a starting point, as it gets bigger and bigger, the temperature and pressure is changing, and as the temperature and pressure changes, the chemistry, the mineralogy itself changes. So we can have prograde, where the metamorphic grade is increasing, and retrograde, where it's increased and now it's decreasing. And we can see that illustrated, I think, fairly clearly here. The garnet crystal initially grows in a schist, but ends up getting biggest in a gneiss. So start out with a shale, produce a slate, a phyllite. This is the prograde path into schist. The garnet's growing now into a gneiss. The garnet's getting bigger and bigger and bigger. And now we're going down in pressure and temperature and back to a low-grade metamorphic rock. We can see where this occurs in this diagram. In a low temperature, high pressure metamorphic zone, within a subduction zone, we're going to see a relatively low temperature prograde retrograde path. Whereas in this case, in a subduction zone where the minerals get forced down into the subduction zone to higher temperatures and pressures, we're going to see that here in the mineral makeup of the rock as it goes from high grade back to retrograde. So the path here is going to take place at higher temperatures generally than the path we see here. When we talk about plate tectonics and metamorphism, we need to discuss the exhumation rate of mountain ranges. That's going to show a relationship between tectonics, the orogeny, the building of the mountains, the climate, how fast the mountains are worn down once they pop up. This is going to control the flow of metamorphic rocks to the surface. As climate wears mountains down, what's beneath the mountain, the root of the mountain, begins to reach the surface.